lecture. I was actually following the lecture, and I modified the documents that I uploaded to Blackboard. So you'll see that in Session 7, there's a document labeled 7A and a document Session 7A and excuse me, 7B and 7C. There's no 7A, just 7B and 7C. I did that to distinguish it from one that I changed quite a bit. Right now on the screen behind me and on your home screen, I have opened the document for 7B. Okay, so before I get to that, I'm just going to run through a quick summary of some of the things that you just covered. Okay, and let me get rid of this thing because we don't really need that right now. Okay, so let's go back in history just a little bit and discuss what we learned up to now. And one of the things that we learned up to now was that a normal distribution has, if we plot it as a density curve or a histogram, it has a bell-shaped curve, right? And most of the values are towards the center. That's why it's so high in the center. The height of that line represents the frequency, the number of people that are in this distribution. You're making a funny face there, you guys. Okay, good. I see what I'm supposed to see. Okay, so the population, you might call this mu, the population mean, and the population, the spread is described by the standard deviation, or sigma, population distribution. Okay, so the mean might be 100, let's say. Standard deviation might be 10. And we know based on that, we know the empirical formula, right? Empirical means estimated or experimental. We know the empirical formula tells us a lot about that population. We know that 68% of the people in this population, or values in this population, or probabilities, whichever way we want to look at it, is between one standard deviation below the mean and one standard deviation above the mean. And we know that 95% is between two standard deviations of the mean, 2 below and 2 above. Okay, so now if we take repeated samples from this population of a certain size, any size, right, we're going to get a new distribution, right? And we take sample after sample after sample, we calculate the means, and then we make a new distribution from all of those means, and we take really a lot of samples. Now, that distribution is also going to be bell curved, except it's going to be much narrower. The middle of that distribution is still going to be the approximately the mean mu. Okay, so I'm going to call it x bar for argument's sakes. Okay, so that mean of repeated samples is going to be approximately the same as the mean, 100, but the standard deviation, right, for the repeated samples, right, is going to depend on the sample size. If you take a large sample size, then each mean is going to be closer to the population mean. Each sample mean is going to be closer to the population mean. In other words, if I take a sample of size, let's say we're talking about blood pressures. If I take a sample of size 2 and I pick pick two people randomly out of the population, I may get somebody with a blood pressure of 80 and somebody with a blood pressure of 105. Right, so I get that average. What does that come out to? 92.5 or something like that, right? And I keep repeating it. I could get two people with blood pressures of 120, right? So each sample result is going to be closer to the mean, but not that. But it still can be pretty spread out. If I took a sample of size 100 people from this range of people that have blood pressures, say between 170 and 130. If I take a sample of 100, well, geez, unless I get really unlucky, I'm going to wind up with a number that's very close to the mean, just by virtue of the fact that I sampled so many people. So if I do it once, I might get an average of those 100 people being 99. And another time I might get an average being 102. So they're going to be really much closer to that 100. The bigger the sample size is, the closer that my means are going to be to 100. So this gets narrower. So we give this name for the distribution for the sample means. We give it a new name called standard error. And the standard error is equal to the population standard deviation divided by the square root of the sample size. The bigger the sample size is, the smaller is the standard error because it's on the bottom of that fraction, right? Bigger the denominator is, the smaller that the value of the fraction is. Okay, so now that we know that property, we can use that property, because now when we don't take repeated samples over and over again, we only get a chance to take one sample most of the time, right? So now when we take that one sample, right, when we take that one sample, if we get a mean for that one sample of, say, 98, right, and we want to know, let's say that sample size, I'm going to call that x bar, is equal to 98. That's my sample mean. Maybe that sample size was 25. Okay, so now if I know that the population standard deviation is equal to 10, right, with that sample size of 25, I know that the distribution, if I had taken repeated samples of all of size 25, I know that the mean would approximate 100 for all of those repeated samples for that population. I really don't know the 100 yet, because I never really know the population. I mean, I'm just postulating that if we took it from this population, this would be the result of the repeated sample means. So now, what would the standard error be? Well, the standard error would be, for if it was size 25, it would be equal to 10, which was the standard deviation for the population, divided by the square root of the sample size. The square root of 25 is 5. It's going to be 2. So my standard error here is equal to 2. So now, having done this, I know that since I know the standard error based on the population standard deviation, I know the population standard deviation, I can then create this range called a confidence interval. I'm going to call it a 95% confidence interval. Sometimes you'll see it as a confidence interval with a alpha over 2 is equal to alpha is equal to 0.05, or alpha over 2 is equal to alpha over 2 is equal to 0.025, whatever. I will get to alpha in a second. I'm sorry I brought it up now. Okay, so yeah, I got it's a little premature. Right? Let me forget about that. Okay, so confidence, we know we can calculate a confidence interval based on what we understand about samples as being, well, 98 is what we know, x bar, plus or minus, well, we're going to predict that since we think the mean is 98, we know how variable these samples can be, right? Because we know the standard error. So we're going to say that based on this standard error, I can expect that I can be 95% certain that I'll actually capture the actual mean if I add and subtract about 2 standard errors below and above the mean. If I want to do it precisely, I use 1.96 times the standard error. Okay, so 98 plus or minus 1.96 times 2, right? So I would add and subtract that. So it would be roughly 94 rather to 102, right? Sounds right? That would be my confidence interval. And in fact, in this case, I would have captured the mean. I would have, based on this sample data, I would have been correct in saying, well, my sample mean was 98, but I know my standard error based on my sample size and my population standard deviation. I know my standard error, so I can predict that I can be 95% sure that the real population mean is between 94 and 102. It worked out for us this time, right? What percentage of the time will it work out for us? It's called a 95% confidence interval, so it's going to work out 95% of the time, right? What percentage of the time do you expect it's not going to work out for you? 5%. So if you do it 20 times, you would expect you're going to capture the true population mean, 19 times out of 20 times. 1 out of 20 times. You're going to be wrong. 5% of the time, you're going to be wrong. Okay, so that's our confidence interval. Now, what did we base this on? We based all this using this 1.96, we based this on what we know about the distribution of the normal, how the normal distribution is distributed, what the probabilities are for normal distribution, and that's based on the empirical formula, or even better, it's based on our z-table, our a table or a function in Excel which gives us more precise values for how this normal distribution is structured. Okay, so now we don't always know that, right? So we have to deal with a situation where we have more uncertainty. We don't know the standard deviation of the population. Okay, now we say to ourselves, if I take a big enough sample size, then the variability within that sample, the actual people in that sample, just like the mean, the variability is going to estimate the variability of the population. So if I have a big sample size, right? I'm going to say 1,000 people, n equals 1,000. If I have a really big sample size, then the standard deviation of that sample, I would expect it to be the same or very close to the standard deviation of the population, right? So if I have a very big sample size, I would just do exactly the same. And I don't know sigma, I only know the standard deviation for those 1,000 people, right? Maybe the population's 1,000,000 people. I only know this standard deviation for this population, for this sample, right? I could say to myself, since such a big sample size, and I know this is such a good approximator of population standard deviation, well, if I don't have the population standard deviation, I'll be satisfied with using the standard deviation for the people in the sample and make believe it's a population standard deviation. So I can use my Z table just like I did before. So in order to use my Z table to do all this, calculate the standard error, calculate the probabilities and the confidence interval and stuff like that, I need one of two things. I need either to know the population standard deviation, or if it's a very large sample, just calculate the standard deviation for the people I sampled. Yes?
I know I'm missing something here, but how come in that case you still have to then use, how come then you're not just saying that the standard deviation is equal to standard error?
Oh, no. Remember, the standard error is different than the standard deviation of the population, different than the standard deviation of the people within the sample. The standard error is the variability if you took samples that size over and over again. It's the standard deviation for the repeated samples of that size. Got it? Makes sense, right? I'm glad you asked that. That's really fundamental. So I'm sure other people are wondering about that too. Okay, so now that you know that, right, that we can get away with using a large sample, we have to make a rule now. What can we call a large sample? Thousands sound like a large sample? Yeah, it sounds like a big sample, right? Sounds like very expensive study, 1,000 people, a lot of time, right? So on and so forth. Drug study with 1,000 people is ridiculous. Nobody would ever do that. Well, maybe they would. I mean, they do these survey type studies where there could be tens of thousands of people in. But at any rate, okay. So now, how about 100? How about 10? No. Okay. Automatically, when there's a big difference, it's easy to tell, right? Okay. But when it gets close, it's a little harder to tell. Our reasoning, we're going to use 30 as our minimum for a large sample. Don't sound like that big a sample, does it, 30? Okay. And not particularly today, but maybe, next week or the week after, we'll talk about the rationale for using 30, picking 30 out. The real reason is that by the time we get to 30, the difference, I'm going to talk about something called a t-score instead of a z-score. The difference between the t-score, which we use when we have a small sample instead of using the z-score, the difference is very small once you get to 30. It gets smaller and smaller. The difference between the t-score and the z-score gets smaller and smaller as the size of the sample increases. And when the sample size is infinite, they're the same. They're exactly the same. You guys don't have to know that. We're going to talk about that later on. The point is that if I have a small sample, I can't get away with using the z-score because I've introduced an extra layer of uncertainty because I'm calculating the standard deviation for the population. I'm calculating it based on a small sample. So now, not only where is the center of this population based on my sample, not only is that one level of uncertainty, but now I've introduced another layer of uncertainty, right? So when I calculate, if I'm working with a sample which is maybe only 9 people, right? Okay, and I take that sample, and now I'm going to calculate my standard error the same way. Standard deviation, except I'm going to take the standard deviation from the 9 people, not from the population, and I'm going to divide it by the square root of 9, divided by 3, and I'm going to get my standard error. Now I'm going to calculate my confidence interval. My confidence interval, just like before, is going to be the mean for those 9 people, right, x bar, plus or minus some number. When I was going to use z, I was going to use 1.96, right, times the standard error. Okay, but now I've introduced this extra level of uncertainty. So I want to make sure that my confidence interval will still capture the mean, even though I have less certainty. So what do you think about that t? You think that t is going to be bigger or smaller than 1.96?
Smaller.
Well, if I make it smaller, it's a narrower confidence interval, right? Which is not going to help me capture the mean. To make up for that level of uncertainty, I want that t to be bigger. Because that t being bigger than 1.96, then I'm adding and subtracting a number bigger than 1.96 times the standard error. So my margin of error, remember that 1.96 times my standard error? That was my margin of error. I was adding and subtracting that. Now my confidence interval can be wider. So my t-score, instead of for a 95% certainty of capturing a mean, my t-score might be 2.5, might be 3, might be 2.1, depending on, it's also going to depend on the size of my sample. The bigger my sample is, up to 30, right? Bigger my sample is up to 30, the closer it's going to be to 1.96. The smaller my sample is, the bigger that t-score is going to be to make up for that uncertainty. Yes?
And as you increase that t-score, you're also increasing from 95 up to closer to 100.
No, it's always 95%. That t-score represents the probability of capturing the mean. You still want to have a 95% probability of capturing the mean based on what your range that you're giving it is. Okay, and since I'm not so sure of the standard deviation anymore, and the smaller sample size, the less sure I am, you got to make that range wider to be 95% certain. Okay, it doesn't change what the real population mean is, just changes the range that you're predicting is going to contain the 95, the real population mean. Let me just go online and make sure I got any questions. Hang on a second. Okay, yes,
So N is the sample size.
you got it.
And when we're talking about, the mean of the means and the standard error of the means, we never talk about like the number of times, the number of samples of N that
We only take one sample. In other words, the idea of repeated samples, that is something we look at to understand how sample distributions work. To understand that when we take a very large sample size, if we had done that many times, what it would look like. And that helps us to predict, if I take it one time, what I can expect in terms of the uncertainty if I take a sample of size 25. What I can expect in terms of the uncertainty if I take a sample of size 100. That's what my standard error really is. It's my variability of, if I had taken another sample, what I would expect in terms of variability for the next time I take a sample. But I only actually take the sample one time. Okay, but that idea of, the sigma over the square root of n, that's the distribution of every sample size, infinite number of times taking a sample. And if you had based your normal and created a normal distribution based on all of those new numbers, right? Those means for each one of those samples. Okay, and that we do that because we want to understand the dynamics of sampling and how it affects the way we can predict what the real mean is.
So if you did N 30 or bigger, so that means you only had 30 samples out of total. You have, 95% population though? Like if you were to do more sampling, like however many times you felt like, and over 30, you would be, 95% confident would fall into that interval range.
What we're doing is you're going to do one sample,
Right.
and you are going to use that one sample to base a range, to calculate a range that you can say you're 95% confident that the real mean falls into. Okay, you're only going to do it once. The idea of the repeated samples is only kind of a construct that we use to understand how samples behave. Okay, so you're only going to do it once, and if you do a sample size of 100, right, you can be more confident than you can have a narrower range, right, for two reasons. One reason is that your standard error is going to be divided by the square root of n, so the square root of n is going to be a bigger number, so your standard error is going to be a smaller number. So you're multiplying 1.96 times a smaller number, so it's going to be narrower. But the other reason is because if you got a sample over size 30, you have some confidence that you know the population mean, population standard deviation. But if you have a sample size under 30, you have to make some more adjustments. Okay, so what's the adjustment going to be? Okay, how do we calculate our confidence interval? Our confidence interval is going to be x bar plus or minus, right, and the z-score, right, times the standard error. If we have a proportion, it's going to be p cap plus or minus the z-score times the standard error. Okay, only difference is over here we use sigma over the square root of n to calculate the standard error. And over here we use the square root of p times 1 minus p over n to calculate standard error, right?
Sorry, I have one more question.
Sure.
So, like, with 30 being the minimum for P, like, if you were trying to estimate, like, something for the entire population of the United States, you could still only pick 30 Americans that were.
Oh, you can use any sample size you want.
Really?
Yes, but in other words, take a look. We have n in all of these, right?
Right.
We can take any sample size that we want over 30, and we can use the z-score with one of these formulas. Okay, because it'll give us enough of in reality, you might want to use a bigger sample. I mean, 30 is kind of an arbitrary number. Not completely arbitrary. When we go on and compare the two tables, the t-score and the z-score, you'll see that 30 is not really that arbitrary a number for a large sample, but it is an arbitrary number. Somebody picked it out and said, hey, let's use 30. Okay, they could have said 50, right? And they would have been better off if they said 50 probably. Would have been even better off if they said 100. But it's a starting point anyway. Okay, you can make your own judgment about whether the sample size is big enough to use the z-score or not. You can still calculate a t-score that's different than the z-score for every sample size up to infinity. When you get to a sample size of infinity or everybody in the population, then the z-score and the t-score are the same. But then you know everybody in the population, so what's the point of sampling? Right? So it doesn't make, you're never going to be in that situation. So you usually only sample once. But in practice, I think it's going to be easier to understand, conceptualize this after you practice this a little bit, after you do a few examples. Okay, so now the next point that we have is, what if we don't know the standard deviation and it's a small sample, right? Well, then we're going to use a different formula. X bar plus or minus the t-score times the standard error. And over here, same thing with p cap plus or minus. Well, we're never going to do that. We're always going to use the t-score, the z-score. Why are we always going to use the z-score for a proportion? What was one of the rules, one of the assumptions that we made when we talked about a proportion sample? Has to be bigger than 15 in each group, right? It's 15 yeses and successes, 15 failures. So all the people in the group adds up to 30. You're always going to have a sample size over 30 when you do a proportion. So you're always going to use the z-score when you're calculating confidence interval for a proportion. Okay? Let's work on a real problem or a real fake problem as it happens, right? We never really work. I don't think we ever really work on real problems. So, okay, it was recently St. Patrick's Day. right? So I'm getting away from zombies. We're not going to talk about zombies next week. Okay. I'm sorry to hear you're disappointed. You randomly sample 40 New York City pubs on St. Patrick's Day and find that they average an inventory of 42 types of beer. You want to know how many beers that the average pub would inventory. You calculate standard deviation for these pubs from your study data. In other words, you have 42 numbers, right? Excuse me, you have 40 numbers, and you take the average for the mean, and you calculate the standard deviation for those 40 numbers. Because you don't know, for all of the pubs in New York City, you don't know the mean or the standard deviation. So we don't know sigma here. But we do know that for the 40 pubs we sampled, that the standard deviation is 6.3. Okay, so is 42 mu or x bar? Average of 42 types of beer. Is that mu or x bar? That's x bar, right? Because it's a sample mean, right? Its mu would be the population mean, which is not known, so that would be x bar, right? Everybody agree with me on that? Okay. Is 6.3 sigma or the standard deviation? Is it the population standard deviation or the sample standard deviation?
The population.
No, sample, right? We got that from the sample, right? Okay, remember, you calculate standard deviation for these pubs, not for every pub in New York, just for those 40 pubs. That's the standard deviation. But the sample size is greater than, right? What's the sample size? 40 pubs, right? So the sample size is greater than 30. So we're allowed to use the z-score instead of the t-score. Okay, calculate the standard error for repeated samples from this population of size 40, and that's equal to sigma, or in our place, the standard deviation over the square root of n. I can use standard deviation because it is, t-score is smaller than, because that's the only thing we know. We don't know population standard deviation. So what's that going to be? It's going to be 40 divided by the square root of the sample size, which is 40. I'm going to get my calculator out. And I'm going to check on you guys online in a second. Let's see, 40. Square root of 40 is that. I'm going to put that into memory. Clear. And what was the standard deviation again? 6.3 divided by, pretty close. Standard deviation looks like it's pretty much 1. Am I right? Did I make a mistake? I'm right? Okay. Standard deviation, the standard error rather, is approximately 1. It's over the square root of the square root of sample size. Oops, excuse me. Standard deviation is 6.3 divided by the square root of 42. 40. Yeah, sample size. Excuse me. I'm confusing myself here. It's approximately 1. Okay, so the standard error is equal to 1. Calculate the 95% confidence interval for the beer inventory in the average pub in all of New York. Now we're looking for remember, we're always looking for the population mean, right? Calculate the 95% confidence interval, and what's it going to be equal to? It's going to be equal to x bar plus or minus, right? 1.96, and why am I using 1.96? How can I justify that? Because it's a large sample, right? If I knew population standard deviation, I could justify it also, even if it were a small sample. In other words, if sample size was 25, but I told you the population standard deviation was such and such, then you could justify using the z-score, even though it's a small sample. So it's either, not both, right? Okay, so 1.96 times the standard error, which is 1. Okay, and what's x bar was 42. 42 plus 1. So it looks like the 95% confidence interval is 40 to 44, roughly. So we're 95% certain that the average New York City pub, right, if we look at the entire population, the average entire population of pubs is carries between 40 and 44 beers, different types of beer. Okay, so now let's take a look at this again, except this time we're going to look at a small sample. You repeat this study in Brooklyn in 16 pubs. You're only looking at Brooklyn now, you do it in 16 pubs. You find a mean of 34 beers, I first made this problem up a long time ago, and Brooklyn was kind of like, like bridge and tunnel kind of area and stuff like that. Now Brooklyn's a hot spot. They probably got twice as many beers in bars in Brooklyn than they have in the ones in Manhattan, right? So I should update this problem a little bit, maybe to reverse the two of them, make the top one Manhattan, the bottom one Brooklyn. But at any rate, you got 16, you got 60. Now your sample size now is 16, right? N is equal, whoops, excuse me. Why is it doing that? Come on, don't jump to the next page. There we go. N is equal to 16, right? And what is X bar equal to? 34, right? We sampled them. Some had 27, some had 41, so on and so forth. X bar is equal to 34. And what is my standard deviation equal to? 7.1. However, my sample size is small. But I still have to calculate a standard error, and I don't know what it is for the population. So my standard error is still going to be 7.1 divided by the square root of the sample size, which is 16, which is 4, divided by 4. Okay, and what's that equal to? It's equal to, let's get my calculator up again. It's going to be 7.1 divided by, whoops.
1.77.
Yeah, 7.1 divided by 4. 1 point, you're right, 1 point. I'm going to call it 1.78. 1.78 is our standard error. Okay, so now what's my 95% confidence interval for the mean number of beers carried by pubs in Brooklyn? It's going to be X bar, right, which is 34, plus or minus, okay. Well, now I'm going to hold off on this because I can't use the z-score. I can't put 1.96. I got to put a t-score in there. Okay, maybe at some point we'll be able to talk about where this t-score comes from. Okay, and a guy who used a pseudonym called Student. It didn't come up in the lecture, I don't think. Okay, yeah, we're kind of getting a little ahead of it. We're getting into the application portion of what you learned in the lecture. Okay, times the standard error. We know what standard error is. It's 1.78. So we need this t-score. Now we know this t-score is going to be based on the sample size, right? Because the smaller the sample size is, yes.
Yeah, what's the cutoff? 30?
30, yes. So this is only n is equal to 16. So the t-score we know is going to be based partly on the sample size, because the smaller the sample size is, the less certain we are on the actual population standard deviation that we're estimating using this. So we got to make this t-score bigger to make our confidence interval wider, to make up for our uncertainty, make sure we really have a 95% chance of capturing that mean. So where am I going to get this t-score? We go back to our book and get a table. Okay, and I'm going to use, you can find them anywhere. This is a table from one of the textbooks that we've used. It's not the one, it probably is similar, but it's not the one specifically that's in your textbook. So what's that? Is it? It's on session 7. There in the second down below, you have the table there. Okay, so let me blow this up just a little bit. Okay, so let's take a look at this. So we see that there's different columns for different confidence interval. This column represents 80% confidence interval. This column represents 90%. This column represents 95%. Okay, let's take a look at what it says in that column. Confidence interval 95%. Right tail probability 0.025, 2.5%. Well, why is the right tail probability only 2.5% for a 95% confidence interval? Well, that's the nature of the beast, right? When we take a confidence interval, right, we're 95% certain that the mean is between those two numbers. But there's 2.5% chance it's below and 2.5% chance it's above the range that we gave it, right? So, and if you look at the normal distribution, we're looking at that middle 95%. So if there's 5% left, since it's symmetrical, 2.5% is in the bottom, 2.5% is in the top. So this is telling us that the right tail has 2.5%. The left tail has 2.5% in it too. So altogether, it's a 95% confidence interval. Okay, so that's why they put that in there. Sometimes they won't show you this top 80, 90, 95% On a chart, they'll just show you the right tail probability or left tail probability. Just keep in mind that like if they just only show you one tail, you got to double it. You got to look to the one that's twice that. So at any rate, okay, half that, right? So at any rate, so let's take a look at this. The other number, we're going to work with this middle column. The other number we're going to use is degrees of freedom. We use the term degrees of freedom when we calculated the standard deviation in Excel. You remember what we used, how we defined the degrees of freedom? It was the sample size minus 1, right? One of the ways you might consider looking at that is if you have a sample of size 1, how many degrees of freedom do you have? You have none, right? You only have that number. If you have sample size of 2, you have 2 numbers, you have 1 degree of freedom. You get one or the other number. Sample size of 3, you have 2 degrees of freedom. This one or that one, and so on and so forth. So it's normally the sample size minus 1. What was our sample size here? 16. So how many degrees of freedom? 15. So we're going to go across here on 15, and we're going to find the t-score that we need to use is 2.131. Right? So I'm going to go back to my calculation, and I'm going to say that t-score has to be 2.131 times my standard error. So what's my 95% confidence interval going to be? It's going to be 34 plus, and let's calculate this. Let's see, 2.131, but there's nothing that's less easy to use than a calculator on a computer, right? You would think they would have a better way to do this, right? Okay, so memory plus. So there's a perfect app for a computer. If you can find a better way to do this, I guess now that they have touch screens like Windows 10 or something like that, maybe this will work out a little bit better. Okay, so that's my t-score times my standard error. Okay, and now I'm going to add that to. Did I put that in? It's in memory. I'm going to add that to 34. And my upper bound is going to be 37.8. And I'm going to subtract it from 34. And my lower bound is going to be 30.2. So 30.2 to whatever number I said that I don't remember already.
37.
Yeah, I'll take your word for it. Whatever it was. Whatever that number was. That is my 95% confidence interval. It's wider than it would have been if I used 1.96, right? But it has to be wider because I have less certainty when I calculate I don't know the population standard deviations. I have that extra uncertainty. Let's take a quick look at this table. If my sample size were 22, what would my t-score be? 2.07. If my sample size were 29, what would it be? 2.05. If my sample size was 30, it would be 2.04. Not very different than 1.96. If we're 50, it'd be even closer, 2.0. If we're 60, it'd be 2.0. If we're 8, see, there's a little bit of diminishing returns here for the sample size. So that's why we use 30. Because as we go up in sample size, it's a kind of a diminishing returns. Yes?
So if you have a sample of 100 and you use a t-score versus a z-score, you're more accurate?
Yes. Yes. You are more accurate in terms of you can more depend when you say you're 95% confident that the true mean is between those two numbers. Well, you are more accurate in saying that. In other words, if you had used for a small sample size like 15, if you had used the z-score and said, "Oh, I'm 95% confident it's between these two numbers," that's not really true. You're you're less than 95% confident, right? So you need to make that wider to make up for that level of uncertainty that you're adding because you don't know the population standard deviation.
And that's reflected by the fact that 1.94 is a little bit higher than 1.96.
Or yes, exactly, for the sample size. In other words, these t-scores, as you get to a smaller sample size, you have to make that interval wider. And the t-score makes it wider for you, so that you have more confidence that you really have really got the range that the mean is going to be within. right? And you can see as you get a really small sample size, the t-score really blows up. Okay, obviously, 1 degree of freedom is just a sample of 2, so that would probably never happen, right? Almost never be in a situation like that. Okay, so that's how this works, right? It really isn't all that hard. You just have to recognize when you use the t-score and when you use the z-score, and you do the same stuff. Okay, so let's move on. Okay. A secret undercover Department of Health and Mental Hygiene study of randomly selected restaurants on St. Patrick's Day finds that the number of slices of corned beef on the lunch specials were as follows. Okay, that's the bottom there. 15 is Katz's. I was just I went to a movie. There's a new theater on Houston Street. Right, it's like a block away from. I think it's Sunshine something or other. It's like a really nice theater. Kind of, the neighborhood's still kind of a little dicey, but it's a nice area. But it's a little kind of it's East Village. When I was young and we used to go into the East Village, it was really a wild area. It's nothing like that now. But it's going to be all high rises and condos in 5 years anyway, probably. But there's a few places that haven't been pushed out yet. There's a place called Schimmel's. Jonas Schimmel's. He makes the what do you call it? Yeah, Knishes. That's a really good place. If you get a chance, go in there. And there's also Katz's Delicatessen, which is one of these places. Have been there forever. And you go in there, they give you a little ticket when you go in there, and they stamp it, and you have to hang on to your ticket. If you lose your ticket, you're in big trouble there, because they write down all of you've eaten, and on the way out you pay for it. And I think they technically say they only take cash, but if you really claim you have no money at all, they send you in the back, and they still take a credit card. So at any rate, just so you know that. So at any rate, they're one of these places that makes there aren't too many left anymore. Make these like monstrous, like pastrami and corned beef sandwiches and so on and so forth. So at any rate, not corned beef, brisket. No, brisket's kind of like corned beef, right? Yeah, it's not. Yeah, exactly. It's not different, much different than. It's really different from pastrami, but it's not that much different. So, at any rate, so here's 10. Here's 2, 4, 6, 8, 16 of these places that they were inspected. This is the number of slices of pastrami that you got on your sandwich. Okay, so now, what are the assumptions that we have here? It's got to be a random sample. They got to be independent. Like, in other words, they're not all from the same chain of delis or something like that. And we're gonna actually calculate the mean. Okay, let's go ahead and calculate the mean. So now I happen to have I think I made an Excel spreadsheet of this. Yes, we have an Excel spreadsheet of this. Okay, you don't have to use the Excel spreadsheet. You can just do it with your calculator if you want. Let me blow this up. Okay, so I'm going to calculate the mean. Mean is equal to average, parentheses. I'm going to take these 16 numbers. Okay, 10 slices roughly is the average. Okay, that's X bar. It's X bar because it's a sample, right? Doesn't represent all the delis in New York, just those 16 we sample. Okay, now let's calculate the standard deviation for the sample. That's going to be equal to standard DEV parentheses, and I'm going to take those same numbers. And the standard deviation is equal to 3.12. And the sample size, N, is 16. We sampled 16 places. Okay, so now I'm asking you, what's the 95% confidence interval for the true average for all the delis of this kind throughout New York City? Okay, so let's see what that's going to be. It's going to be X bar, right? X bar plus or minus. Okay, and what's it going to be plus or minus what? Well, it's a small sample size, and we don't know the standard deviation for the entire population of delis, so I have to use the t-score. And what is the t-score for a sample size of 16? I think it was, what did we just used it, right? 2.131 times, right, times the standard error. And we're going to calculate standard error. What is the standard error equal to? Okay, standard error is equal to, let me do it this way. Standard error is equal to the standard deviation for the sample, because we don't know the population, divided by the square root of the sample size, 16. Okay, and that's that's 0.078. Okay, so now what is my confidence interval? My confidence interval is going to be equal to my mean. Where's my mean? My mean's up here. Plus 2.13131 times my standard error, which is 0.78. Okay, now I can do this. I don't need parentheses because it's going to do the multiplication first and then add it. So I don't have to worry about that. If you're concerned, you can always put parentheses around here just to make sure if you're worried that Excel might misinterpret it. Okay, and that's going to be equal to 11.72. And I'm going to repeat this again, except I'm going to find the lower limit of my confidence interval, which is going to be 10.0, equals 10.06 minus 2.1131. I regret that I didn't put this into actually type it into another box, times my standard error. So the average, we're 95% certain that the average number of slices that you get on a pastrami sandwich in New York City is going to be between 8 and 12 slices. Okay, so now you know all about pastrami. Had I told you that 3.12 is the population standard deviation, or if we had gotten a sample size of 30 or greater, you could have just used 1.96 instead of looking up the t-score. Okay? Okay, that's the only difference. Yes.
I'm sorry, so question for you. Again, what is 11.78.39?
11 point, that was my upper limit. That was X bar plus 2.131 times the standard error, times 0.78. And the bottom one, when you watch this on the video and stuff like that, you'll be able to get a chance to look at this. Let me find out if these guys online are still there and can hear me. You guys still there? Awake? Capable? Moving? Okay, good. Thank you. All right, good. Just wanted to check. Okay, so that's not so bad, right? Okay, so in practice, this is not unreasonably difficult. The concepts, because you can tell that, this is a new concept. The idea that you got a distribution, which is the population, and you got a different distribution, which is repeated sample averages, and so on and so forth. It is a difficult thing to comprehend in the beginning when you're first being exposed to this. As you work with it, it will make more and more sense. Keep in mind the t-score for every sample size, 1 through infinity, there is a different t-score, right? We only worry about the ones for sample sizes 30 and under. But you can see from that table, there was a different t-score for 30, 40, but there actually is a different one. And really what happens is that for each sample size, you have a different t distribution. Like you have your z distribution with 1.96, right? It's 95% of the outcomes, right? Well, now your t distribution, you have a specific one for 31, for sample size of 32, for sample size of 33, sample size 34, sample size 35, different one. It'd be impractical to put all of them in a book. So they give you that one table because they know most of the time you're only interested in a 95% confidence interval, a 90% confidence, 99% confidence interval. So those 3 columns and those sample sizes are usually good enough for you to deal with. So most of the time, 30 and over, you can use the z-score. If you want to be more precise, if you have a sample size of 40, you can still use the t-score. Nothing says that you have to use the z-score in any case instead of the t-score, right? The only time you would use the z-score instead of the t-score, because you knew it would be exactly the same outcome, is if you knew the population standard deviation. Anytime you're dealing with a sample, the t-score is more accurate. In fact, if you imported this whole thing into Excel, into SPSS, and did this calculation, I'm going to do that right now. Don't save. Do I have this? Yeah, don't save. That's good. Don't save is good.